All right, so we've been talking about properties of radicals and how to simplify radicals. In this lesson, we're going to talk about properties of exponents and how those apply to radicals as well, because we saw in the last lesson that radicals are just a fancy way to write exponents. So here are some of the rules. I would take a second to write these rules down. We can multiply things with exponents as long as they have like bases. This is going to be the common thing. As long as they have like bases, we can do a lot of things with them. So a and a, same bases. A to the m times a to the n is a to the m times n. Here are some examples of these on the right side as well. A to the m over a to the n is the same as a to the m minus n. So when multiplying things with like bases, you add the exponents. When dividing things with like bases, you subtract the exponents. When you do a power to a power, you multiply the exponents. You can also take a power and distribute it into a parentheses, whether through multiplication or through division. Negative exponents we saw in the last lesson is the same thing as writing an exponent as a fraction, right? Moving the variable to the opposite side of the fraction. And any single item to the zero exponent is equal to 1. That includes anything in parentheses is equal to 1. So if I have more than one thing in that parentheses to the 0 power, that's equal to 1. Here's how we can apply those. I hope you wrote down those rules. This top one looks like the first rule, the multiplication rule. Y to the 2/5 times y to the 3/5. They have the same base, so we can add the exponents. That's y to the 5/5 equals y to the 1. The second one, 6a to the negative 1/2 over 6a to the 3/2. That's the same thing as the second rule. We can subtract the exponents. Negative 1/2 minus 3/2 is 6a to the negative 4/2. That's the same thing as 6a to the negative 2. And then the last rule on that sheet had to do with negative exponents. That's the same thing as 6 over a to the 2. Because a was the only thing to a negative exponent, it was the only thing that got moved to the other side of that fraction. Whenever you multiply things, as long as they have the same index, right, a nth root and an nth root, you can multiply them into one radical. So here, for example, square root, we can multiply those and make it a square root of 36. As long as the indices match, we're allowed to multiply to combine. The same thing works in reverse. I could take that 36 and break it into 3 and 12 if I wanted to. For example, simplifying this expression, x to the 9th. So the last lesson, what we saw was, what we could do is we could take that x to the 9th and write it as square root of x to the 4 to the 2, and that's the same thing as x to the 8th times x, which is x to the 9th. All right, the way that we're going to look at it now, we're going to look at it a little bit differently, is we're going to take that x to the 9th, and for any, I wish that we had started one slide later. What we're going to do is for any simplifying that we're going to do with a radical, we're going to try and find pairs here because we have an index of 2. That's telling us how many is in a pair. And we're going to break this down into its prime factors. So x to the 9th is the same thing as x, 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 x. Count those, there's 9 of them. And since the understood index is a 2, we're looking for pairs. And I like to use the analogy that this is the buddy system, that buddies get to go outside. So 4 of those sets of buddies get to go outside, and this one lonely guy here has to stay inside. The things that get to go outside get multiplied, so those times those multiplied gives you x to the 4th. If you had more than one thing inside, you would multiply them to get the inside. Outside multiplies to get the outside, inside multiplies to get the inside. All right, same thing here. The 4th root of b to the 7. What I would do is I would write that out. It's the 4th root of b, b, b. There's 7 of them. And since it's a 4th root, 4 is the index, I'm looking for groups of 4. There's a group of 4. There's not another group of 4, so I can't buddy up anybody else. But buddies get to go outside. We're using the buddy system. Since I started with a 4th root, I'm going to end with a 4th root. And the things left inside are those 3 guys. B to the 3. That's my final answer. Take a second, try this one. If you listed out all 7 W's and all 9 Z's, and then found groups of 3, you would have 2 groups of W's and 3 groups of Z's that got to go outside, and then 1 lonely W that had to stay inside. The underlined portions there are what's going outside. Buddies get to go outside, the buddy system, as if you were in Boy Scouts or Girl Scouts. Simplifying numbers works the same way. We just need the prime factors. So for example, for 56, I would say 56. I can break it down any way that I want. I'm going to end up with the same exact prime factors at the end of the day. So you're thinking of anything that will divide 56, and 56 is divisible by 4. It's actually 4 times 14. 4 is not prime. I can break it into 2 and 2. Those two are prime. 14, I can break into 2 and 7. All right. Write out your prime factors in numerical order. That's 2, 2, 2, and 7. And if you want to make sure that you're correct, you can multiply in your calculator 2 times 2 times 2 times 7, and it should give you back 56. Now, the understood index is 2, so I'm looking for groups of 2. Notice I have buddies here. So those buddies get to go outside. Inside, 2 times 7 is 14. It's the same concept as when you have variables. Just now we have numbers. We're still breaking into as many prime factors as we can. Once we get down to prime factors, I circle those so that I know they can't break down any further. So the square root of 24. When you break it down with a factor tree, it doesn't matter what factors you start with. You should end up with 2, 3, 2, and 2. Or the same thing as 2, 2, 2, and 3. I like to write them in numerical order. Find your buddies there. There's a group of 2. Remember, we're finding groups of 2 because the index is 2 there. That group gets to go outside, and 2 times 3 inside makes 6. 6 square root of 50. So what we really need to know is what's the square root of 50? I don't know. Let's find out. Square root of 50. 50 is 5 times 10. I can't break 5 down, but I can break 10 down. And so my prime factors are 2, 5, and 5. There's some buddies. This guy doesn't have a buddy. So what I'm left with is 6, the same 6 I started with. And then the blue underlined part is 5 square root of 2. 6 times 5 is 30. So 30 square root of 2 is my final answer. All right, toughie. We've got a little combination of everything. The square root of 40, I can break that down into 8 and 5. 8 is 4 and 2. 4 is 2 and 2. And so my prime factors, including the x's, y's, and z's, I've got 2, 2, 2, 5, x, 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 y, 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 5 of those because it's y to the 5th, and z to the 7th. 1, 2, 3, 4, 5, 6, 7. All right, how many in each group am I looking for? Since the index here is 3, I need 3 per group. And so I have a group of 2's, x's, y's, z's, and in fact another group of z's. Remember that buddies get to go outside. So outside I'll have a 2, x, y, z squared. I'm going to keep the same symbol that I started with. Since I started with a cube root, I'm going to end with a cube root. And the things left over are the things that did not get buddied up. Here's another. Okay, so we can use the same operations that we had on the very first slide, the rules for combining the exponents. So here, a to the 7th over a to the 3rd, this is the same thing as square root of a to the 4th, because 7 minus 3 is 4. That combination rule said with division we subtract the exponents. The square root of a to the 4th we saw in the last lesson, same thing as square root of, well, we can do it the same way we have been. That's the same thing as a. Look for buddies. I've got 2 sets of buddies, so that's the same thing as a squared. Technically, by the last lesson, it's equal to the absolute value of a squared. Remember when we're taking an even root, that matters. With a square root and even root, it really matters that we have that square root. We're leaving that off here for convenience, but just know that absolute value, it actually does matter. All right. the cube root of 3 over 81. What I could do is simplify what's inside the cube root first. That's the same thing as cube root of 1 over 27. 3 over 81, same as 1 over 27. You can divide both those items by 3. Then the cube root of 1 over 27 is just 1 over 3. All right, a few more. 7 square root of 50 over 10. We actually just did the scratch work to figure out what square root of 50 was 2 slides ago. 50 breaks into 5 and 10. 10 breaks into 2 and 5. So we end up with 5 square root of 2. What I'm going to do is take that 5 square root of 2 that's in blue and sub it into this part that's underlined in blue. Everything else is going to remain exactly the same. The 7 over 10 stays the same. Now, 7 times 5 is 35. And 35 over 10 simplifies to 7 over 2. So my final answer, 7 square root of 2 over 2. One more example just like that. This is the last one. First, take the square root of 300 and break it down. 300 breaks into 3 and 100. 100 into 10 and 10. Each 10 into 5 and 2. So we should end up with, in all, a pair of 2s and a pair of 5s that go outside to make 10. And a 3 left over lonely inside. That 10 square root of 3 in blue is going to replace the square root of 300. The 2 over 300 is going to remain the same. On the top, 2 times 10 makes 20 square root of 3. And then 20 over 30 simplifies to 2 over 3. In the next lesson, we're going to keep working with these radicals. We're going to continue working with radicals and exponents.